forgot to record the class in the beginning, no problem. Yeah. This is a voltage of a sensitive load which has been connected. This is a sensitive load. Sensitive loads. And we are improvising the voltage at the point of common coupling by a device which is connected in a series. We just come back to what kind of the device it should be. See, you generally know that, you all people know about when there is an outage in completely a line, we can have an UPS. Okay, if there is completely an outage over here, that means that there is a you can consider a switch over here, hardly having out this feeder impedance, and there is a switch. If this particular line is completely outage, what is the device which is going to connect over here? It is, we connect an UPS over here, uninterruptible power supplies. I mean, it have actually, I mean, the UPS, maybe if you look into the particular to the UPS, maybe it is going to this sort of the connection will be there. When there is an outage, then obviously this is going to come into picture. This is like going to come into picture. That is the UPS is going to come into picture. Okay. Yeah. You know that the UPS can support a sensitive load. The only it's the UPS whatever you are going to connect to a system or to connect any kind of a loads in your households also. We hardly connect a light and then the fan also. Okay, we cannot able to support from the UPS in the entire the house also. If at all, if you want to make out to support the entire vicinity or entire consume, then we require to have a higher power rating of the UPS. Okay, but see, if this is a device, here there is no outage. We are just having in our case what we are being going to study is there is no outage. There is still a series connection. There is no outage. There is a fault occurred at this particular point. Okay, fault occurred at this particular point. The drop will be there. That is the reduction in the magnitude of VT2. In this case, we are connecting a device of a series device. This is going to correct the voltage. Maybe assume at this particular point, it is just going to bring back to the nominal voltage of a 1 per unit only. Consider now, this is the, this is the voltage actually. This is the voltage which is going to correct by your this particular device. Okay. Now the VT2 plus the series, whatever the magnitude reduction is there, series, which is going to add to this voltage and make us to the, in terms of the magnitude, which is going to make to the VT1. Now what happened is the magnitude increase in the voltage at a point of common coupling. This voltage VT2 plus VSE is the voltage at a point of common coupling during the sag or during a T2 condition. In the case of the pre-sag voltage, the VT1 is very much equivalent to the PCC voltage. It is very much equivalent to the VT1. Okay. I mean, when your system is idle, the one is represented to a pre-sag conditions. One is represented to a pre-sag condition. At that particular point, it is equivalent to the PCC one. Now, we are looking out the power calculations. When your series device is correcting the voltage to a value of a nominal voltage, in that case, what is the power variations? Now, this is the voltage which is added by your series device This is the device which is going to correct the voltage at the point of common coupling VSC. Okay. Now what happened to the IL2? This is the current which I have given. This current is during the sag, during the sag, during the sag, without VSC, that is without the series device. Okay. Now what happened was, when you have a series device, when we have started injecting the VSC, what is going to happen? It is going to increase the current, because the PCC2 voltage is equal to VT2 plus VSC. Then obviously it is very well equivalent to VT1. Then what happened was, the current is going to increase. The current is going to increase, and the angle which is there is with respect to the this voltage alone, with respect to the VT2 bar plus VSC bar. Then the IL2 is going to come over here. IL2 is going to come over here. This is IL2 magnitude, is the magnitude wise, the IL2 magnitude is equal to the magnitude of the pre-sag current. This is the current when this is the current when you are when the series compensator or a series device is starts operating. That means that when you are injecting this voltage of VSE, the IL2 is very much equivalent to IL1. Now, if you make out the powers here, one thing is, this is the at the VT2, there is a current which is flowing here, it is IL2. Okay, with the VT2 voltage, the IL2 is flowing out here. From the source, what is the power? It is of VT2 phasor and then the IL2 phasor conjugate. Okay, it is going to happen as the VT2 bar of VT2 into IL2 into cos phi plus j times of VT2 into IL2 of sin phi. Okay, this is the source power. And now this series voltage is also if I draw the series voltage is also this is VSE, which is this is a del, and there is a current flow is also will be there. The IL2 is an angle of phi. Okay. Now the series device is also having a contribution of VSE into IL2 star. Then this is going to as VSE into IL2 times of cos phi plus j times of VSE into IL2 times of sin phi. Okay. Now, if you add the total load power, SL is equal to SS source power plus the series compensator device. What you get is VT2. To add these two equations, we get as VT2 plus BSE into IL2 times of cos phi plus VT2 plus BSE into IL2 times of sin phi. Okay. Yeah. Now this VT2, again, this is very well equivalent to the magnitude of VL1, as we have seen, like with respect to the magnitude, which is going to about VT1. Then it is of VT1 into IL2 times of cos phi plus VT1 times of IL2 times of sin phi. Whereas we are expressed it as The IL2 is very much equivalent to IL1 when your CA VSC starts operating. Okay, that means that this is of the VT2 is very well equivalent to VT1, and IL1 times of cos phi, J will be there, plus J times of VT2 into IL1 times of IS phi. Okay, this is very well equivalent to the power okay, just a simple arithmetic. What is the important point which I would like to convey over here? It is, this is an important expression. It's an important expression. Like this is the device, series active power filter device, which is injecting some amount of the real power as well as the reactive power, Okay, this is something like a PSE, the PSE plus J times of QSE, And this is about the series active power filter. See, this is the power actually which is required by this compensator, Okay, what I was explaining about the UPS, it is almost all similar to this compensator, which is to be used to correct the voltage sag, Okay, but whereas in the UPS is going to start functioning when there is an outage. But this is a device of a series device which is going to operate even under the sag conditions. Okay. When you say about this one, when you look into this particular equation is the SE, that is a series active power filter. Is injecting some amount of the real power to a system as well as the reactive power of a system. Okay. Okay. This thing which we'd like to yeah. I mean, this particular device, which is has to inject the real power as well as the reactive power into a system. Okay, real power as well as the reactive power system. When you're talking about the real power, when you're injecting into a real power, it should have some kind of an energy storage. Some kind of energy storage. About the reactive power, it doesn't require to the energy storage also. In just if you connect some kind of a capacitor over here, and if you try to operate by some means of a device, if you are trying to make out a device which is going to correct the voltage inline, maybe this is the part which I was trying to make out. Okay, this is the source over here. When you try to make out the correction, if you try to make out the VSC, okay, with the capacitor, when you are saying about a capacitor, it tries to inject only the reactive power. But as such, like when you are looking about the phasor diagram, it looks like the injection is voltage correction is possibility is the injection of both the real power as well as the reactive power. Okay. Now we cannot make use of this particular kind of a device. If at all, if you want to use this particular kind of a device of a capacitor alone, it cannot support this real power. It cannot support this real power. In order to support this real power, we need make use of a standby source, an AC source, which is connected to a rectifier over here. We can able to make out this is a if you want to maintain, this is a rectifier, a rectifier, rectifier, and then this way, this is another additional source. Okay, we can't make use of this source alone as an input for this rectifier. Why? Because is the system itself is under the in a weak condition, because a system has experiencing the fault. Because of that only the terminal voltage, it got affected, or it got reduced in the uh, reduction in the magnitude of the voltage. During that condition, we can't make out this source alone to drive this an inverter. This is an inverter only. Okay, we can't make use the power transfer to this way again the same thing. Okay, we can't make out this kind of the possibility. We have to use an additional a standby source to charge this capacitor. Instead of this, we can go for the batteries also. Okay, we can go for a batteries also. Can go for a batteries also. Like whatever the way which the UPS is there, the same thing, a similar way, you can make use of the UPS itself to correct the voltage. But thing is, the device which has been used here, which is of having an inverter, I mean, obviously we need to use the battery. It is very well straight away we have been understanding it also. We have been understanding it. We need to use a battery because it has to inject the real power. And then when you're using a battery, of course we need to use an inverter only in order to make out a convert a DC to an AC, because we have been looking out the voltage correction in an AC system. We are looking out the voltage correction in an AC system. We have to use an inverter. Okay. Yeah. This is about some of the power calculations, or in order to understand what kind of the device to be kept over here to correct the voltage set. Now the question is, why cannot we use, as I said, like in the earlier classes, especially when I was discussing about a problems which is related to the voltage imbalance, or something like problems which are related to the why cannot be used this particular device, what I mean to say, the device is having a battery, and this battery, which is of an inverter, and this is going to connect to a line. This may be the line I can overdraw over here also, a transformer. We'll come back to the topologies. Okay, the source. Okay, this is kind of a device. I mean, the same thing which I made it out in this fashion. Now the point is, why cannot we use the device to correct the under voltage? Okay, why cannot we use this device as the under voltage? See, this under voltage, it is a long duration kind of a problem. It is a long duration voltage variations. In that case, if at all you want to correct the long duration voltage variation, the battery capacity should be much more higher also. Okay, this long duration, this under voltage is more than 1 minute of a problem, is more than 1 minute of a problem. In that case, it requires a huge storage device, like what the UPS is. The UPS generally in a system, for you take for your desktop system, the UPS maybe hardly supports you have been using about a 0.5 kV or 1 kV UPS. It supports maybe 30 minutes, not more than that also. if we want to increase this, the voltage support or anything like more than 30 minutes or 1 minute, what we require to is we require to increase the battery storage element also. Even this device, whatever I was explaining, is to correct the sag, but not the under voltage. Why? Because of the limitations in the energy storage also. Because of the limitations in the energy storage, this device cannot be used for the under voltage problem. Why? Because the sag itself, it's hardly, the definition says it's about a 0.5 cycle to a 1 minute, to a 1 minute. In that case, the battery storage, because the system it get restored within the 1 minute. I mean, most of the cases, if it is not a typical fault, generally whatever the fault which have been there, within the 1 minute they will try to isolate they'll restore it back to a normal condition. Okay. In that case, mm, I mean, to have the energy support by this inverter to a 0.5 cycle to a 1 minute, it is more than enough. I mean, people are working out in a way of to have the energy storage also. Okay, especially in the distribution level, they have the batteries also. Okay, people are working out in that directions also. But typically, what we are looking out to the device is the device which we are going to look into that is going to supply the mitigate the voltage saturated power quality issues. Okay, but not the under voltage. The limitation is the only this particular battery. Okay. Uh, if you are interested in this particular topic, there are case what they are trying they did was this is a very important area people have been worked out also. What they have done is see, there is a typically the faults which have been occurred is mostly like a three-phase symmetrical fault alone is a common fault. But if there is a fault occurred in a single phase only, this voltage, this phase of A is a fault. Phase of I mean just giving an explanation. This is a fault in a phase A. Then obviously the A phase voltage has reduced, but the VB and VC voltage are in a healthy condition, In that case, what they try to do was they try to take the power from the B phase and then the C phase power, and they try to correct the voltage at the A phase also. Okay. I mean, the explanation is if there is a voltage reduction in the A phase alone, this phase B and phase C are in a healthy condition. They try to take out without going for a battery, without going to the battery. They try to take the power from the B phase and C phase. They're trying to going to correct the A phase alone. There is, as I remember, there's interface. I mean, AC voltage corrector, something like this name. Okay, this kind of the possibility people have been worked out also. Okay. Now, what we were been understanding is we've been understanding like for the case of a voltage sag, we have looked for the power calculations, power calculations, power calculations, power calculation, that is the real power as well as the reactive power with respect to the source power, with respect to the source power, as well as the series compensator or a series device compensator, and we just make out to the load powers also. Okay, with that we understood that the device which are going to use for the series active power filter should have the battery and or even the capacitor also. The capacitor has to be self-supported by an external external source. Okay. Yeah. Before going to that, just a minute. Yeah. This is a typical single phase compensator. This series compensator will also be called as a dynamic voltage restorer. Okay, it's a dynamic voltage restorer. Okay, this is we have a from the inverter point of view, we have a current source inverter and then the voltage source inverter. This is the current source converter, and which we have been trying to, instead of the capacitor, we are going to use over the inductor, and this particular inductor is also it requires to have the self-sustained also. I mean, during this particular if you consider this particular point of Vs, if there is a voltage reduction, then we are going to correct the voltage at the critical load point of view. Are you able to see my pointer over here, right?
Yes, sir.
Yeah. Yeah, this particular point at the critical load bus, after this VC, we are going to correct the voltage at this particular point. Okay. Yeah. I mean, you can see that the functionality actually with this, when you have the current source converter, we have been blocking the reverse blocking of the current. We have been making out the current direction in a unidirectional. We have been just using this the reverse voltage blocking alone. Okay, we can able to operate this way of the topology. Okay, and then the rest of the case, it is going to operate this way. Okay, this way we are going to operate. Yeah. And next is about the typical voltage source converter based DVR, which has a self-supporting DC bus, the CD, which is there, which is supporting a DC bus with a large DC capacitor. Okay, it's a large DC capacitor. It has become more dominant since it is lighter, cheaper, and expandable to the multi-level and the multi-step versions also. Okay. And then here, especially with respect to the inverter, there are the different topologies which have been there. We can go for the higher level of the inverter also, depending upon the power level of the distribution, power level of the system also. But generally, going to the typically 2 level is appropriate also. It is more than enough to go for the distribution level voltage level. Yeah, this is a device which is of a three-phase, three-wire DVR, three-phase, three-wire DVR. We don't have a neutral over here. We just, I will try to explain you about how the operation of this particular inverter is going to operate in order to correct the voltage at the terminal voltage also. Okay, this is a, I'm just going to give about uh, the clarity of what kind of the device which is there. It has a, this is an inverter, this is an inverter, and this is having the, typically it is a three-leg inverter because we require to have a three-phase system only. This is how it goes. This is a to filter out the any switching harmonics. We have been using the LC filter over here. LC filter is over here, and then this this is another leg which is connected to the phase B. Here is another leg which is going to connect to the phase C. All other points, which is the neutral of the other phase of this transformer, which is going to connect over here this way. Okay. Is about the three-phase DVR connection, three-phase DVR. But this capacitor, it has to be supported by an external by the battery also. The battery is connected to the capacitor also. This way it looks like. When it comes to the voltages, the supporting level, we have a rectifier supported, and then the battery supported, and then the capacitor supported. I mean to say that this particular capacitor, which is required to support from an external source while correcting the voltage or while injecting the voltage VCA, VCB, and VCC. During that, to support the capacitor voltage, we require to have a left rectifier supported. Rectifier supported, I mean to say, rectifier supported in the sense like we have just now seen in the earlier case. Yeah, this particular case. You're able to see this screen, right? OneNote screen, right?
Yes, sir.
Yeah, yeah. This particular source is an AC source, which is there. We are being connected to the rectifier. Okay, there is no battery over here. There is no battery over here. That particular case is about the a rectifier supported. Okay, this is a rectifier supported. In other case, instead of the rectifier, we can go for a battery also. We can go for a, without this rectifier, we can go for a battery also here directly. The capacitor, which is supported, I mean, you can have a in between. I'm sorry. This capacitor, maybe hardly we may be having the a DC-DC converter, a DC-DC converter, and then the battery over here. This way also it can have the possibility. That is of the battery support. And this capacitor supported is again this particular methodology of making out the capacitor supported is not appropriate. Why? Because during this particular, I mean, people have been maybe the initial stages they have been understood in a wrong way also, or wrong perception also. Because of that, they have been labeled this as a capacitor supported. What is the capacitor supported in the sense like instead of using the rectifier unit and then the capacitor unit what they try to do was the capacitor because now this particular device in order to correct the voltage is going to supply the real power as well as the reactive power what they try to do was they try to take the power from the source itself to maintain this particular voltage, capacitor voltage, and then they try to redistribute that power to a system to correct the PCC voltage. Okay, there is no rectifier and there is no battery. They try to develop an algorithm to maintain this capacitor voltage, some value of the capacitor voltage. Once you are able to maintain the capacitor voltage from the source itself, then your inverter starts functioning to correct the voltage at the PCC. It won't be any problem. Thing is, the source itself is in a very weak condition because it is experiencing a fault. In that case, charging the capacitor or taking the power from the source to maintain the VDC is not the appropriate solution. It is not appropriate. It is not a correct solution also. Okay. Why? Because see, once your inverter is started functioning to correct the PCC voltage, once your inverter starts functioning to correct the PCC voltage, then obviously this much amount of the real power as a reactive power is going to inject the system. If this device, the inverter, it starts injecting this amount of the real power, the capacitor voltage is going to decrease. You know that very well also. Whenever you connect just a capacitor and short the capacitor, it's going to discharge in very faster way also. What I mean to say that if alone you use the capacitor alone to correct the voltage, the VDC is the capacitor DC link voltage is dropping out also. Because of that reason, we cannot make out this kind of a capacitor supported kind of this topology. This topologies of rectifier supported and the battery supported is a very appropriate, a very correct solution to correct the voltage sag. Okay. Yeah, in the next class, we'll try to see one of the algorithm and one of the topology we'll try to take out, and we'll see that how we are going to make out the voltage sag quality improvement also. Before going to that, I try to discuss about the voltage swell kind of at a voltage swell condition also. How does the power relation looks also? Okay. Okay then. Next class is on tomorrow.